Okay, ji. Welcome to this session. This is uh, this is going to be recorded. We have two agenda points. One is that we'll be going over some basics of graphs, which we covered over the last couple of lectures in the recorded ones, and we'll be like going over some of those concepts. And the second thing is that we'll be talking about, which is our new topic. We'll be talking about types of graphs, which is quite interesting and easy topic. So let's start with the recap. And the board of questions is that I'll try to keep an eye on the chat, but if I fail to answer some chat questions, you can switch on your mic and interrupt us. And जो लोग इधर available in class with, you can obviously interrupt as a regular class. So let's start with the fundamental definition of graphs. So one graph is a discrete structure which is composed of two components. One was set of vertices, other one is set of edges. So we talked about two types of graphs. They may be directed ones, or we can have undirected graphs. So the difference between both types is dependent on the nature of edges which we have. So if we have a graph where each edge in the graph is a directed one, the line segment between two vertices has an arrow on it notating the direction. That means that we are talking about some one dimensional or one directional traffic. And in undirected versions, we can have traffic in both of the directions. Okay, so the because I'm going to go over some of the terms which we talked about in our recorded sessions. So one term was adjacent vertices. So meanings of adjacent vertices are the vertices which are neighbors of each other. And more specifically, we mean immediate neighbors. So in terms of graph theoretic concepts, the vertices which are connected directly using an edge. So if I have a vertex A and a vertex B, A and B are neighbors of each other. So B is adjacent of A is adjacent of B because the graph is undirected. So adjacency is the concept which essentially captures the immediate neighborhood of two vertices. So for example, if I have third vertex C, so A had two adjacent vertices B and C. If I have a fourth vertex which is connected with B, so D is not adjacent to B. D is not an immediate neighbor of A. So adjacency list of A will only take care of B and C and won't be storing the relationship with D directly because D is not adjacent to A, or conversely, A is not adjacent to D. In other words, they are not immediate neighbors of each other. The next definition which we talked about in one of our previous session was path. Okay, yes, say it again. C and D are not adjacent to each other. Yeah, so that line is called edge, right? So if there is a direct edge, which means by immediate neighbors, we mean that there is a direct edge between any two vertices, right? So any two immediate neighbors are adjacent vertices, and if they're not immediate neighbors, they're not adjacent, right? So let me keep this graph as it is, and within this graph, let's talk about another concept, which we talked or termed as walk. Walk was defined as a sequence of vertices such that in that sequence, ith vertex, vertex number I in the sequence, and vertex number I plus 1 in the sequence, they make up an ordered pair, and that ordered pair is part of set of edges. So now if you look at this graph, which is in this brown color, so if you focus on the relationship between A and B, so this edge which is between A and B can be written as A comma B. So this ordered pair is notating one edge, right? Because the graph is undirected, we can also write it as BA, which means that order does not matter, right? We can go from A to B, or we can go from B to A. So each ordered pair notates one edge. So in the context of walk, when we say sequence of vertices, that means that we'll be writing many vertices, v1, v2, v3 in a sequence going up till vk. In that entire sequence, the emphasis is on sequence, the order of the vertices in that list. So if I pick any pair of vertices, so if I pick the first pair v1, v2, if I pick the first pair v1, v2, so I is 1, I plus 1 is 2. So v1 comma v2 must be an ordered pair in the set of edges, right? So if I'm talking about a walk, so only those vertices will appear in the walk where they have an edge in the set of edges, right? So this walk has intuitively exactly same meanings as that of uh, what we use in our daily life, right? So for example, if I asked you to take a walk from one location of Lahore to another location of Lahore, that means that, so for example, if I start from Lums, I'm writing sequence of vertices, right? So if I write some point Lums, I write some point, let's say H block, I write the next item as Gulbarg, and let's say I write the next item as motorway, right? M2. So in this sequence of 4 items, let's analyze each of the consecutive pair, right? So when we say vi comma vi plus 1, so if you look at the first pair, Lums comma H block, that means that these two locations must be directly connected on the map. If they're not adjacent to each other, I cannot jump from Lums to H block. In other words, there must be a road which I'm notating in graphs as an edge. So there must be a road from Lums to H block. That means that Lums and H block are adjacent to each other. Then when we move, when we slide this window forward, we say that H block and this part, these two vertices, H block comma Gulbarg, they should also be part of the set of edges. So if there is an edge from H block to Gulbarg, which means there is a road on my map, then I can take that route. If there is no map, if there is no direct road from H block to Gulbarg, then I cannot walk along that possible path, possible route, right? So taking a walk from Lums to M2 means that I'll start from, so in the graph which is given on the right side of this notion, if I relabel them, so I start calling by these locations as, let's say Lums is location A, H block is B, Gulbarg is sorry, let me retitle them. So let's say Lums is in this example C, H block is A, Gulbarg is B, and M2 is D. So if I write now if I rewrite little cleanly, these blue words, they were C, A, B, D. Focus on the definition of walk. This is a sequence of vertices. C, A, B, D is a sequence of vertices. Why I was able to walk over that sequence? Because every pair was adjacent to each other. There was a road between them. BD have a road between them. CA have a road between them. So that sequence matters, right? So sequence of locations which will take me to that walk will have the same meanings as that of in the context of graphs. Are we okay? Do we have any questions till this moment? So moving one step forward from this definition was the definition of path. So path is a sequence of vertices. Again, it follows or fulfills the restrictions of a walk, that in that sequence, all those intermediate vertices should be reachable from each other. They should be adjacent to each other. And in the path, so path has two parts. One is that this is walk. So path is a type of walk. The restriction is that vertices cannot be repeated. So there is no repetition of vertices. When we say vertices cannot be repeated, that means, so let's like talk about an example. So there are two things which we should keep in mind before moving to the next screen. It is a walk. Within the walk, all those conditions you have just talked about the walk should be met, but repetition of vertices is not allowed. So if I draw a graph, yep, absolutely, yeah. So if I like make a slightly bigger example of six vertices, so there could be multiple connections between them, right? If I label them as A, B, C, D, E, and F. So now if my start point is C and my target is D, so I can take this route. I can start from C. I can go to E. I can go to D. So one possible walk could be C, F, E, and D. So if you focus on this walk, is this a walk? This is a sequence of edges, sequence of vertices which are next to each other. When I say sequence of edges in this context, that means the same thing. That means that we are talking about sequence of roads which are connected to each other. And there's no repetition of vertices. So if you focus on the names of the vertices, they're C, F, E, D. So each vertex is unique. So there is no repetition. So hence it's a path as well. If I think of an alternate possibility, that is that let's say we start from C, we go to B, we go to E, go to F, go to C, go to B, and go to D. So this is another walk, which was C, B, E, F, C, B, and D. If you focus on the start and end points, this also fulfills the purpose of walk, that we walk from C to D. But if you have like taken a notice of the visualization and also the if you take notice of the stuff which is written in the sequence, so B is repeated, and what else is repeated? Sorry, C is repeated. So repetition is not allowed. So this is a walk, but this is not a path. So this is a walk and path as well. Moving one step forward, and then like we can take a small pause if you would be having some questions. So if I start from C, I go to F, go to E, go to D, go to B, and go back to C. So now if you focus on the black line, this is essentially making a loop. We started from a point and we have returned to the same point. So except that one corner point where our start and end point are meeting, remaining the intermediate vertices are not getting repeated. Such kind of walk is called cycle. Right? We call it a closed walk because it takes us back to home where we started from. And the additional stuff is that the part which is getting repeated is the start and end point. And that is kind of point which cannot be avoided. Its repetition cannot be avoided, right? Because our target was to reach back to our home station. But in the intermediate steps, F, E, D, B, none of them are getting repeated. So cycle is an extension of path where we connect our last point to the start point. We go back to home. And rest of the restrictions remain same, that repetition of vertices is not allowed. Okay. Do we have any questions till this moment? Yes. Okay, in closed walk, we can repeat intermediate vertices. So for if I write this cycle in the color black, so we started from C, we went to F, went to E, D, B, and C. Now in this entire sequence of vertices, the only thing which is getting repeated is C and C, which is allowed because that was our target, that was our objective to reach back to home. Right? But in the intermediate vertices, nothing is getting repeated. So it's a walk, it's a closed walk, but it's a cycle as well. Now, let me try to walk through a closed walk, which is not a path, which is not a cycle, which means that intermediate vertices can also get repeated. So if I start from F, go to F, sorry, I start from C, go to F, go to E, go to D, go to B, E, D, B, and F. Now, if I write this whole sequence, this is C, F, E, D, B, E, D, B, and C. So these two things are fine because we are interested in the cycle, right? But if you look at the intermediate vertices, there are many points which are getting repeated, right? So B is getting repeated, E is getting repeated, D is getting repeated. So that's not allowed. So it's a closed walk. The pink one is a closed walk, but not a cycle. Make sense? Okay, let's do one small thing, small trick with the path, and then we'll move to the next concept. So this is a graph of yes, someone raised hand online.
Sir, I had a question. Could you please explain what your ICP say? And like you have the shortest walk, like closed walk, it has to be a path. And इस तरह के वो उनको जो proof करना था, could you please explain that कि उनको proof कैसे करना था?
Okay, sure, sure. Just give me a while, right? So after this example, I'll go over that proof as well.
Okay.
So if I name these vertices A, B, C, D, E, so okay, so let me so our problem is that we are interested in a path from C to B, right? So if I'm interested in a path from C to B, one possibility could be that I start from C, go to E, go to D, go to B. So C, E, B, C, E, D, and B is a path. Are we all okay that this is a path from C to B? This is one of the paths. There could be many paths. There's a direct path as well. There's a path using one vertex as intermediate vertices. We opted for the path which is of two vertices. Now, from a path, in this particular path, which is written in red color, how many edges did we consume? How many edges are there which we have used in the path? We have used three edges, and so those were these edges, 1, 2, and 3 edges. So if we had 4 vertices on a path, if we had n vertices on a path, n minus 1 edges will be required, right? So now only one like step, somewhat very similar to what we did in induction. So if I want to convert this path uh, to a cycle, so I can do if there is an edge from B to C, I'll add that one edge into it. So previously we had n minus 1 edges, and now we are adding one more edge. So we have moved from n minus 1 edges, we have added one more edge, and our cycle has become CEDB. So we also add this edge. So the total number of elements in the path are now 5. Number of edges which have been consumed, they are, yeah. So technically, like I'm little incorrect. So when I say total number of elements, they are looking 5 because C is repeated twice. So actually number of vertices which are on the cycle, they are 4. Number of vertices which are part of the cycle, they are 4. Previously, number of vertices which were part of the path, they were also 4. So we have evolved a cycle out of the path by adding one more edge from the last vertex to the starting vertex, and that didn't change number of vertices, but that has changed number of edges, and the resultant is a cycle, right? More specifically, this is the kind of property which we'll be covering in our today's new discussion as well. That's in cycle, if there are n vertices and all of them are part of the cycle, then there are n edges, right? If we have n minus 1 edges and n vertices, then it is guaranteed that there can't be a cycle, right? So if I go to that question which was just asked about that the shortest walk is a path, right? So walk is between two endpoints. So we have a start point, we have an end point, we call it target. So we have a start point, we have a target point, and we take some number of steps to go over there, right? So because this is a walk, so this tilted curve shows that there could be many intermediate vertices. So one possibility is that there were some vertices, and because this is a walk, repetition is allowed. So we might have taken some repetitions from some intermediate vertices. We might have gone this way, gone back and went forward, or gone back, forward and back again and again, and using some loops in between. So when we think of path, that means if there is a walk, that means that there is a possibility that we can go from S to T, right? So when a walk exists, that means this sequence of vertices exists, one V1 V2 up till some, so I can call it Vs and Vt. From the source to target vertices, there's a sequence of vertices which exist because walk exists. Now, is this the shortest one? It totally depends on, so how many items are here in the sequence. It depends on the repetition of the items, right? So if we don't repeat any item, that means our number of repetitions, number of items in the sequence will start getting shortened, or length of the sequence will start getting shortened, right? So if we keep on doing that exercise again and again, and we remove all repetitions, that means that when we write a sequence from Vs to Vt, all items in between are going to be unique because we have killed all repetitions, right? As we keep on removing the repetitions in this entire process, we'll keep on reducing length of that sequence. And the last sequence, which does not contain any repetition, is the shortest possible sequence which exists from start vertex to the target vertex. And because it's a walk and it does not contain any repetition, so hence it's a path. So in other words, the walk, which is the shortest one in terms of number of hops in between, the shortest one will be the one which does not contain any repetition. That will land us to a path. Yes. No, okay. We're saying shortest walk is the path, right? So our claim was, I hope this claim was correct on the part of that ICP as well. But like we're saying, the shortest walk is a path. So when we say a walk has been given, we'll keep on removing the repetitions. When we keep on removing the repetitions, our connectivity still remains intact. The resultant is a path, right? Shortest path is a slightly like different thing. And we'll be talking about that thing as well, probably by end of this session or next session. Can you be a bit loud? Okay. I don't think we had 4 edges. So if I quickly redraw that thing, there we had four vertices. Was this the case? So probably we talked about this kind of thing. Okay, I can have one more over here, right? So if my target is that this is my source and this is the target, I want to find a path. There could be multiple paths, right? So one path could be that I follow this one, right? So how many vertices are in the sequence? 4. What is number of edges in the sequence? 3. So for n vertices, n minus 1 edges, that means there's no cycle. If I just put one more edge in that sequence, my number of vertices are not changing, no? I'm connecting the last vertex of the sequence. No. So hold on, right? So I'm okay. In the sequence, we're writing a fifth vertex, which is actually the same, which is the first one. What does that mean? That means that we are looping around. We have gone back to the step 1, right? So this orange part is representing a cycle. It's a cycle from source to source. Now, if you look at this cycle, how many vertices are there as part of the cycle? How many vertices are there on the cycle? How many edges are there? Does that clarify that thing? Okay. So someone asked a question there. Path is a subset of walk. Okay, path is a sequence, right? Path is not a set. In sets, we don't really care about the order. When we say sequence, that means the order matters, right? So path is a sequence. Path can be a subsequence of walk with no repetitions, right? Okay, थोड़ा सा आगे चले. So two vertices are called adjacent vertices if they're immediate neighbors of each other, if there is an edge between them, right? So two vertices are called connected vertices. Two vertices U and V are connected if there exists a path between U and V. We know path, right? So U and V are connected if there exists a path. Are you connected with Facebook? right? Are you connected with anything online? That does not mean you have some dedicated channel between you and Facebook, right? But that means that there is a sequence of so many, maybe millions of intermediate hops in between, and you are eventually connected. In other words, there exists a path from your node, from your machine, from your mobile or computer to the server which hosts Facebook, right? So what does the path mean? That means that sequence of vertices, that sequence is important. You are connected with the Wi-Fi which is installed somewhere in this room. That is installed with some other router in the building. That router is connected with the probably LUMS server. LUMS is connected with some other internet provider, and like there is a whole sequence, right? Including the sequence which goes in the ocean, right? Which usually gets like eaten up by the dolphins and all that stuff, huh? Whatever they are, right? So, but see, when like the sharks eat up that connection, you get disconnected, right? Which means that there's no sequence from you to Facebook now. Why? Because that particular edge has been disturbed. So from a path, sorry, from a path, if we remove one edge, the path will break down. From a walk, if we remove an edge, it's not guaranteed that walk will break down because it might be part of some repetition, right? So, but in path, we have unique possibilities. So two endpoints are connected if there is a path. So does this thing like make sense? That what do we mean by the notion of connected vertices? Two vertices are connected. So there could be two possibilities. One, like if you think of this whole connectivity in the terms of induction, the base case could be that two cases are directly connected. They are adjacent to each other. If they are adjacent to each other, so that is the simplest possible connection. They are connected. But two vertices can be connected using lot of intermediate vertices. Okay. So this is what a pair of connected vertices mean. Yeah. So like the one example was your node connected with some server, right? So, and if you look at this visualization, so if for example this is some PC in the lab and this is server on LMS, so they are obviously not directly connected. So there is a network between them, right? So if there is a like possible way where we can send some message from PC to the server which hosts LMS, so that means that path is working. If path gets disturbed, then we won't be able to send our messages or receive our messages. So I hope it makes this notion of connectivity clear. Okay, a graph is connected. Yes.
सर
So
अगर हम कोई एज जो है वो रिमूव नहीं कर रहे तो फिर तो आपके हमारे सारे ही कनेक्टेड नहीं होंगे वर्टेक्स।
from a path,
जी सर।
जी अगर अगर पाथ है ना, देखो ना मतलब एक अगर पाथ है, ये आपका कंप्यूटर नंबर 1 है, यूजिंग सम नंबर ऑफ एजेस यू आर कनेक्टेड विद कंप्यूटर नंबर n. So if this is a path, that means no edge is getting repeated. If you don't remove anything, then path will remain intact. But if one of the edges gets disturbed and this was a path, then 1 and n will get disconnected because there was no duplicate. Because this path, okay, so what should I say is that if there was only one path between 1 and n and it gets disconnected by one edge, then 1 and n are no more connected. Does that like address your question? Okay. What was your question? Which has a which graph G is a mm-hmm, mm-hmm.
We add any one edge to it. Does this necessitate that there exists a subgraph which is a subgraph?
You're absolutely right, and that's what we will study today, right? Right. Yeah, but yeah, your comment is completely correct. And like we'll make sure to reach at that point, and probably you can help me to recall that thing. Yeah, we have reached that point. Okay. So a connected graph is a graph where every pair of vertices is connected. What do we mean by a pair being connected? When we say one pair is connected, that means there exists a path between the elements of that pair. When every pair is connected, that means the whole graph is connected, right? What does that mean? Let me try to draw some examples, right? So for example, if this is a graph, this is the same graph which we talked about. Is this a connected graph? Is every pair of this graph connected? Is every pair, let me name them, right? So if you can find some pair which is not connected, is every pair of this graph connected? No. Which pair is not connected? B and A. What is a connected pair of vertices? What do we mean by connected pair of vertices? We've just done on the previous slide, right? Yeah. So does there exist a path from B to E? BDE or BCE, two paths. We can, like, we are interested in at least one path. Yeah. Okay. So the graph is connected. What if I add one more vertex into it? F vertex. Is the graph connected now? This is no more connected because there's no path from F to any other vertex. So because connected graph means that all pairs are connected.
सर पाथ के अंदर हम एक एजेस के ऊपर 2 दफा रिपीट कर सकते हैं?
देखिए, अगर आप एज के ऊपर रिपीट करेंगे तो you'll be automatically repeating vertices, क्योंकि edge is an ordered pair of vertices, ना? When you start writing that thing, तो वो edges repeat होना शुरू हो जाएंगे. Are you getting my point?
सर अगर आप एक एग्जांपल से थोड़ा सा समझा दें.
Sure.
समझ.
So let's say I start from B, go to C. So I'm writing it as B, C. I go to E, and then I go back to C, and then I go back to B. Can you see it? Now, if you like, I've repeated an edge twice. That essentially means that what was the first red line? That was CE. Then on the return, it became EC. So vertices are automatically getting repeated if we are going over the same edge twice. Right. So our fundamental definition of path, that in the sequence no vertex will be repeated in the path, that will get violated if we repeat the edge. Okay. A graph can contain a connected component. This is the last part of our recap part. Connected component is a subgraph. What is a subgraph? We talked about in the first session of graphs. Subgraph is part of the graph, right? So for example, if I have, let me draw a quick example. So if this is a graph, so I can pick any part. So for example, this is a subgraph. This one vertex is also subgraph. This whole thing is subgraph. There could be many subgraphs, right? Subgraph is one like part of the graph which contains the relevant edges and vertices in that part. So subgraph has somewhat very similar meanings as those of subset or kind of thing. So connected component is a subgraph. The second part is that that subgraph must be connected, which means within that subgraph all pairs are mutually connected. And the third restriction, which is very important, is that subgraph is maximal. Maximal means we are talking about maximum possible, largest possible. Right. So let's keep these three conditions in mind while talking about connected components, that it is a subgraph, or it's a connected subgraph, and it is maximal. It's maximal connected subgraph. Now, what does this whole thing mean? What do these three conditions imply in terms of graph? So let me try to draw an example. So we have 7 vertices over here. Okay. So I claim, what is a connected subgraph? That in that subgraph all pairs are mutually connected, right? So I claim, and you have to tell me whether my claim is correct or not. I claim that this part, this red part, is a subgraph. Is it a subgraph? Is it a connected subgraph? which means within that subgraph, all pairs are mutually connected, not necessarily directly. There exists a path from one vertex to another pair, to another vertex. Is it maximal? By maximal, we mean that this is the largest possible subgraph which can contain these three vertices. In other words, I cannot add a fourth vertex which will increase size of the subgraph while maintaining its connectivity. So what if I try to include this blue vertex into the red part? So if I try to include the blue vertex in the red part, that means I'm talking about this subgraph. Is it a subgraph? Is it connected? Is it maximal? So because it's connected, so part one of the discussion is that my previous answer was incorrect. The subgraph which I showed at the start, this one, was not the corrected component because it was not maximal. Why it was not maximal? Because further maximum was possible, right? So it's just like you have been given an array of numbers. You say that number 5 is largest. When will your claim become false? If you succeed to find another number which is larger than 5. Right? So same is the case that orange subgraph was not maximal because we can insert one more vertex into it while maintaining its connectivity. Is the red one now maximal? Is it a connected component? It's not, because it's not maximal. Why? Because we can add one more vertex. Sorry, we can add one more vertex into this, and now this entire subgraph which is in the blue part is corrected. And we'll keep on increasing. We can bring in this vertex into it, and we eventually bring every vertex into it, and all of them become like the whole graph is a subgraph of itself. It is connected, and that is maximal. Why is it maximal? Because we can't further expand its size. Does that like make some sense? Yes. Yeah, that's what was this example, right? And let's do one more example with a slightly different kind of connections. So how many connected components you can see over here on this graph? This contains how many vertices? 6 vertices are there. How many connected components are there? Can't I say 6? What if I put every vertex in a separate component? Won't it be a subgraph? Won't it be corrected? Won't it be maximal? See, if I start with this like kind of claim that this is a component, this is a component, this is a component, this is a component, this is a component. So all these components fulfill the first part, that they are subgraphs. They also fulfill the property of connectivity, because they are connected with themselves. Within the subgraph, all connections are there, right? Every vertex is reachable from itself in step zeros, in step 0 as the base case, right? So are these pink boxes maximal boxes? One of them is yes, this is maximal because it can't be further expanded. We can't insert any new vertex into the center one, and while preserving its connectivity, because we can't add any other further connected vertex within this component. But these two can be merged as one component, and these 3 can be merged as components. So number of connected components are 3. Yes. Yeah. So see, okay. So given a graph, given a map. So for example, you are some policy analyst, and you are analyzing Google Maps, and more specifically, you are analyzing that which part of the country are not connected with another part of the same country by road. So for example, if you analyze map of Pakistan, so probably if I may be wrong because I don't know much of some parts, but assuming that there is some road which connects some part of the country to another part of the country. That road might be like very bad, very long, whatever, right? Very short. We don't care about that thing. So if the connectivity exists, then the whole map of the country will be part of one thing, right? So now, just give me a while because I've been forgetting that part of the answer. So So now you slightly expand your analysis and you look at subcontinent and you analyze the collective map of subcontinent. And when you like feed stuff on Google Maps, that is there a path from or is Lahore connected with Amritsar directly by road? You'll say no. You'll find no, because there's no road which is allowed, right? Because of that border stuff. That even if there is a road that's closed. So now if you like pick the map of the subcontinent, at least two components must emerge from it, because we know that cities of India are not connected with cities of Pakistan. So we won't be able to like sort of have a like road travel between them. So at least so if within those countries, if there are some parts of the countries which are not connected with other parts, then a number of components may increase, but at least two components will be there, right? So does that answer that part, that it could be a possibility that your entire graph is a full connected component, or may not be, right? So in the worst case, all pieces of your graphs are scattered, right? And your maximum number of components could be same as number of vertices if none of those towns or places are connected with each other. And the best case, it's another extreme, that like if everything is connected, then your number of components are one. Yeah. Yeah, so इस तरह होगा कि like so for example, if you look, let me try to clean it up a little bit. So if you just like assume that this map is representing six locations of six locations of subcontinent. So just to keep it more sort of meaningful, let me make it two places. Like so let's say this part is India, this part is Pakistan, and let's say here is Lahore, and here is some other city of India, like maybe Amritsar, right? So now Amritsar is part of a component, which means Amritsar is paired with other cities of India, which means there's a path from Amritsar to other places of India, and that's part of other component. If you look at the right side part, is it right? Yeah, right side part. So Lahore is connected with some other parts of Pakistan, but not with that component, with any part of that component. If by some magic, if we succeed to insert some edge between any two parts of the two components, then they will become one component, because now this city can be connected with this city using this path. Okay, so by adding one edge between two components will definitely help them to get merged as one component. So does that answer your question? Okay, any other question? Yes. Say it again. Number of vertices? Not really. I can give you a counter example. Like if I got your formula, so can you repeat the formula so that I can show this formula to everyone? And number of vertices minus number of edges. Oh, it's equal to number of connected components. Oh. So, you see, but if I like, if I have like one simple contradiction is that number of vertices over here are 4, number of edges are 4. That means 0 connected components, but there is one connected component. If B is not equal to, okay. So in that case, so what about this one? V minus E is negative number, right? That can't be a number of connected components, right? So such kind of, okay, so the kind of stuff which I'm leaving for all of you is that you can try, if you really got this notion of connected components, which was also covered in the recorded lecture, the second version of the same thing is for directed graphs. Over there, we slightly change the term and we start calling it strongly connected. The notion and meanings, underlying meanings remain same, but because edges are directed, now we need to look explicitly that there is an edge from one place to another, and then another edge comes back to that place. So once you go over there, so there might be some that kind of stuff where we can formulate things with some additional conditions, right? So, and I think like the kind of conditions you are like trying to investigate right now. So you start like sort of expanding that thing. You might be able to land onto something, but nothing is like immediately in my mind that how can we relate that thing, because like so like there could be some like edge cases where this will fail, right? For some of the cases, it may be true. Okay, Ji. Yeah. Yeah, for any tree, trees are the kind of thing which we'll be studying next, but for any tree, number of edges are less than number of vertices. Yeah. Yeah. Okay. So that was the like part of recap which I promised to some of you last time that I will go over that thing again because we were like running in asynchronous mode for the last couple of weeks. So okay, couple of like more points which I wanted to sort of clear up. Somehow repeatedly I kept on hearing this thing from many of you that graphs are something which are like quite bad, quite challenging. Usually people can't solve graph problems in the exam and that kind of thing. So I think whoever has told you that was a completely false kind of thing, right? So even if they were TAs, like they might not be correct in that claim because so as you start playing with graphs, you'll start seeing that they are like pretty convenient, easy data structures, right? So their context was slightly different, right? So last year they like faced some trouble, and the reason was graphs were covered in the last week. And then last week people usually don't like pay much attention, and bulk of exam was about graphs, and like they messed up. So that was probably the logistic reason, not the like reason related to contents. Otherwise, graphs are pretty simple and easy to play with, right? So and we'll keep on playing with graphs over the next couple of weeks by the time we meet the exam, right? So I'll make sure that you get like very comfortable with graphs. And the second point which I wanted to emphasize over here before we move to the next topic was that why are we studying graphs? They are beautiful. That's one reason. The more important, yeah. So there are actually two kinds of reasons. One is which in the previous section, one reason I mentioned was that the greedy reason is that will bulk of exam be of the graphs in final two? Yes. Okay. Right. So the yes was like on a lighter note, right? So I can't commit anything as far as the exam content is concerned at the moment, but we can talk about exam as we go like little closer to the exam. The exam is about like 3 or 4 weeks away from now, on 20th December, right? So okay, yeah, so there are two reasons, two kinds of reasons of studying or loving graphs. One is a greedy reason, like the comment which we saw that you can find them in the exams, you can find them in the coming quizzes, and to sort of make some reasonably good grade in discrete math, you'll have to somehow embrace graphs. Like little more greedier thing could be that the kind of stuff that in the next immediate course there will be component and graphs. But that actually I don't call that like much greedy because that's a little long-term planning kind of thing. So graphs are everywhere. Graphs are the probably the most important component of this whole course, and you can see as you will get into graphs, you'll see that all those fundamental things will start popping in graphs. So graphs are everywhere, right? Our network is a graph. Facebook is a graph. More importantly, the era in which we are living today and the thing which we use for solving quizzes and homeworks is dependent on graphs, GPT, right? So GPT is the fundamental building block of GPT is large language models. When you say models, those models are actually graphs. I'm not sure whether you were like following those news last year or last year when GPT was getting launched. So in the first or earlier versions of GPT or some LLMs, their inventors claimed that they had a sufficiently complex network or model at the backend, which contained billions of parameters. When you say billions of parameters, each parameter is an edge of the graph. So the graphs you use every day in terms of GPT, they have huge number of vertices and edges at the backend, right? So LLMs are heavily dependent on deep learning. Deep learning is composed of neural networks. Each neural network is a graph. So once you like indulge into the domain of machine learning or AI, you'll see graphs almost everywhere, right? So AI is a bit generic, but in the ML component, you will have to play with graphs and trees a lot. That's one very important thing. The second important thing is that if we like slightly, if we for a while, if we forget that we don't like AI or ML and we put them aside, everything else is also graph. So for example, the kind of problems which people use, which people like do and model and plan in terms of networks, distributed systems. So if you're planning to take NetSen in the next semester, you will face graphs again. In distributed systems, you'll meet graphs. So yes, like in terms of computer science and its applications, if you start thinking of anything, so graphs are like very beautiful and attractive and strong, discrete and data structure, which helps you to model a lot of like wonderful applications, right? So like if you're planning for grad school, it might be like helping you to do a lot of like beautiful stuff related to your research and those kind of things, right? So like one small component, like which should give you the kind of indication of the wisdom in the thought process of people who are planning that thing. Uh, we have like two or multiple strong groups in LAMS. One is AI group, other one is networks group. So for the last many years, networks group have been like focusing on like building some innovative stuff. They were in the top 6 in Asia as far as systems and networks research was concerned. Recently they're like most kind of innovative and most productive course in terms of research has been modeled around LLMs. I'm talking about topics in internet research, which has been modeled around LLMs, which means that you can now appreciate the kind of applications. So LLMs are built on graphs. So having a like good grip on the fundamentals of graphs will always give you an edge as you go along, right? Other than this exam, right? This exam is based on luck or kind of. Okay. So now that was the story part. So yeah. There again. Euler graph. Yeah. Some people call Euler. That is fine. Yeah, if you'll ask me, I can definitely go over in the recitation session, but otherwise we'll like that is important. Yeah. Yeah. So in this course, you won't be tested on algorithms, right? Because we didn't study algorithms. We just named them at points that for these kind of problems, those can be applied, just to give you a like broader idea of graph theory. But in data structures, you will definitely be doing that stuff and you'll be coding them as well. And you have an experience, right? Huh? BFS, DFS, but like we didn't talk about that how it works, no? Yeah, so that's why you won't be tested on that part, right? We have a bulk of other stuff where you will be tested on. Okay, अब आगे चले थोड़ा. Okay, so let's go over some like very easy and intuitive and fancy types of graphs. The first type which we are looking at is complete graph. So graph is this type of graph, which is called complete graph, is a graph which is notated like this. So if we think of a graph of vertex 1, this does not have any edge. But if you think of a graph of 3 vertices, in this kind of graph, every vertex is connected with every other vertex. Right? Think of K5, this makes up a star and a cycle around that stars, which means that every vertex is getting connected with every other vertex. We'll call it complete graph. We'll use this notation of Kn. So Kn in the subscript means that this is a complete graph of n vertices. Degree of every vertex is n minus 2, n minus 1. What will be the total degree of the graph? How many vertices are there? Okay, K is name of the graph, na? Number of vertices are n. So each vertex has n minus 1 degree. So n times n minus 1 is the total degree of the graph. So if you have watched those recorded sessions of the last week or this week, where we introduced graphs, we talked about that so how degree is computed? So degree of this vertex is 2. Why? Because there are 2 edges which are incident on that vertex. What about this vertex? Again, degree is 2. But if you focus on this edge, this got counted twice in the degree. At one endpoint, it got counted over here. At the other point, it got counted over here. So in the total degree, each edge is contributing twice. So total degree is n times n minus 1, which is actually 2 times number of edges. So E is a set of edges. So its cardinality is this one, and twice number of edges is the total degree of the graph. So what would be the number of edges in a complete graph? What will be the number of edges? n times, इसी को इधर से हमें नजर आ रहा है ना, n times n minus 1 over 2. And what is this expression on the right side? What does this mean? This means the first ICP. How many edges in KM? So our board of ICPs is same as that of other recorded lectures. So you'll have to like upload these answers over there. But like we got the idea, right? So this is same as n choose 2, which most of you were whispering. But and if you like evaluate n choose 2, what is that? N factorial over? ये क्या होता है? N factorial over n minus 2 factorial, which I'm sure आपने ये फार्मूला आज के लिए याद किए होंगे because counting focused quiz था. And this is what else it comes here? 2 factorial. 2 factorial is 2, and n factorial or n minus 2 is so if you simplify this thing, you will be landing onto this part. Okay, so moving forward on the other type of the graph, a path graph is rated as P. Pn is a path graph on n vertices such that all vertices make up a path. Path is a sequence of vertices where there is no repetition. So if all vertices are part of one path, that means there is no cycle, right? So if you focus on, so sometimes we call them line graphs as well, because if I, for example, redraw P4, so this is like another possible visualization of this graph could be somewhat like this, right? So all vertices appear on a line. So if you like now understand this second characteristic of these kind of graphs is the degree of every vertex is 2 except the endpoints. Endpoints have degree 1 and the rest of the vertices have degree 2 because they need to be connected with the previous and the next vertices. Have you studied linked list in CS200? Okay. So you can think of as a linked list, right? So there is a head, there is a tail, they have only one connection point, and then each intermediate object or node or vertex is connected on both sides. Say it again. Yeah. You are absolutely right. I said, right? Yeah. So okay. So how many edges are there in the path graph? N minus 1, right? So when we have two vertices, they can be connected because it's a path, so they can be connected. Our base case is for two vertices with one edge, and keep on adding one more vertex. You'll keep on. So if I like, let me try to draw some intuitive stuff over here. And I'm sorry for the poor drawing. So if I start with this, now I'm actually getting to what you were saying, right? So if I have a graph, so I have three vertices, 3 minus 1 edges. As I add one more vertex while maintaining its property of keeping every vertex on a path, so the an edge has to be added over there, right? So with every increment, one edge and one vertex are added. So n minus 1 edges are there in this thing, but if I add one additional edge within the same number of vertices, and if I remember correctly, that was your comment. So if I add an edge from the first to last vertex, that will put all of the vertices on the cycle. And your comment was that if I add an edge anywhere in the graph, some cycle will be created in the graph, right? So was this the one? Okay. So I'm sure you're done with the ICP. So how many edges are there in PN? N minus 1. Moving to the next type of the graph, which we have already done, and that's called cycle graph. So cycle graph is the path graph by just putting an extra edge between the last and the first point. So what will be the change in number of vertices in the cycle graph as compared to path graph? There won't be any change, but one edge will be added. So what will be the number of edges over here? N. Make sense? So we usually use Cn for rotating a cycle graph containing n edges. Okay, the wheel graph is obtained. This is slightly like different kind of terminology. We use Wn. So if I focus on the second bullet first, so let's say we are interested in creating W5. W5 means that we create 5 vertices. We put all of them on a cycle. How many vertices and how many edges have been added over here? So number of vertices so far are 5 number of edges are. That's what we have learned from the cycle graph, right? But Wn says that number of vertices in Wn is n plus 1. So W5 should contain 6 vertices. So 5 vertices are around a cycle, making up the like outer edge of a wheel. And then there is a central vertex over here, which gets connected with every other vertex. So in the change, in the next step, where we inserted this new vertex, our number of vertices have changed by 1. And what was the change on number of edges? Previously there were 5. And how many new edges have been added? 5. So what will be the number of edges in a wheel graph Wn? That will be that will be 2n in Wn. Okay. Moving to the last type, not last type, but like another simpler type is star graph. So star graph means that so for example, if you recall the stuff which I talked about at the start of the class, that there is some access point in this classroom which is transmitting Wi-Fi signals, right? And during the classes, particularly, all of us are connected with that thing, right? Otherwise, we get bored during the classes if we are not connected with Wi-Fi. So if there are n people sitting over here, n plus 1 is that access point, everyone is connected with that thing. And so if we are like chatting with each other, usually we are using that access point. So we are not directly connected with each other, but we are connected through an access point. So if you look at S5 or S6, that's that kind of thing, that there is a central hub, there's a central point where everyone else is connected. So this makes up this type. Sometimes these types are also called topologies. So this is a type or topology of a graph. How many edges are there? This has exactly same number of edges as those in path graph, n minus 1. Okay, this is a slightly different kind of graph. It says that we have we've been given an n. N is length of a bit string. So if you have length 1, if n is 1, of length 1, how many bit strings we can create? What is a bit string? A string which is composed of zeros and ones. So if you are restricted to one spot, one sized array, you have to fill it with bits. What kind of bits can be created in length 1? 0 and 1. Length of 0 is 1, length of 1 is 1. So there are only 2 bit strings which can be created of length 1. What if length is 2? 2 raised to the power 2. And what are those bit strings which can be created? 0, 0, 0, 1, 1, 0, 1, 1 are the kind of bit strings. So total 4 bit strings can be created, right? So this kind of graph says that for Q1, this 1 means number of bits which can be used to store or create a bit string. So of length 1 or 1 bit, we have only 2 bit strings, 0 and 1. Okay, and for the kind of length 2, we had 4 possibilities. So for each bit string, we create a vertex. What about if bit string length is 3? How many bit strings can be created of size 3? 8, 0, 0, 0, 0, 0, 1, and you can think of up till 111, right? So 8 bit strings can be created. What about how many bit strings can be created if n is 5? 2 raised to the power 5, right? So for n bit strings, 2 raised to the power n different bit strings can be created. So the way graph is constructed is that for every bit string, we create a vertex. And 2 bit strings are connected using an edge if there is a difference of 1 bit. So for example, if you look at 0, 0, so 0, 0 is connected with 0, 1 because there is a difference of 1 bit. The other bit is same. It is connected with 0, 1 due to the same reason. It is not connected with 1, 1 because there is a difference of 2 bits. So if you apply 2, 3, that gives you a like cubic structure, right? So this is the kind of graph which we call n cube. Now the kind of thing which I did with the previous section, I'll do same thing with you. That what is the number of edges, and I won't reveal them over here, right? So I'm sorry, someone actually asked me to go to the previous slide, but I didn't see the message on time. So can you speak out that which slide you are referring to, or is it still needed? So so how many edges are there in Qn? Try to start making a pattern, and then I'll successfully, I hope I succeed. Yeah, it's not 2n, because when n is 1, 2 raised to power 1 is 2, but your Q1 contains only one edge. So apply your answers on these examples, right? So Q1 has only one edge, n is 1, 2 raised to power 1 is 2. That's one edge, so it does not work. But slight modification over here will start working, and if you start like playing with these 3 examples, you should be able to land onto the pattern, right? Oops. Yeah, that was an accident. I didn't mean that. I hope you didn't see that. Okay, so moving to another interesting type of the graph. So this is the last type, and then I'll stop. Uh, so graph is, have you ever seen this kind of graph? Forget about the text on the slide, just focus on the graph which is there. Did you see this kind of graph ever in your life? When? When functions, right? Absolutely correct. So in terms of functions, we used to draw these kind of graphs where the first bubble on the left side used to notate domain, and the other bubble used to domain codomain, which means that some elements of domain were getting mapped to some elements of the codomain. So over here, like we have in this visualization, we have some applicants. They have applied to different universities. Some applicants have applied to multiple universities. Some applicants are doing chill. They didn't apply anywhere. So it's not a function, but it's a graph, right? So the graph is called bipartite because universities as well as applicants are being notated as vertices, being modeled as vertices, and the applications are being put over there using edges. So if applicant 1 has applied to university 1, there's an edge between applicant 1 and university 1. So the two partitions are there are two parts of vertices, or there are two types of vertices. There is a special characteristic about those two types of vertices, and that is that within, if you focus on one part of the vertices, so this is a subset of vertices, there is no edge within those vertices. If you focus on the second part of the vertices, there is no edge within that part, but the edges are actually going across partitions, and that's why we call it bipartite. So if a graph can, if vertices of a graph can be divided into two partitions such that within one partition there are no internal edges, all edges go across partitions, so then we call it bipartite graph. And if you like focus over here on its notation, so we are explicitly writing LR. L is for left partition, R is for right partition. So these two components are making up set of vertices. Their union is all vertices, and then we have edges, right? So bipartite graphs have many applications. People have used them in literature for beautiful applications. For example, we can store the data of actors working in different movies, artists for albums, and those kind of different relationships. If you look at the last one, this is like example of computational biology where we have different metabolites and reactions. People might be having drugs on one side and diseases on the other side, and then they could be mapping that what kind of drug has an impact on curing a particular disease, and those kind of relationships are used over there. There is a famous theorem which is called marriage theorem, where on one side we have men, on the other side we have men, and that's a possible matchmaking kind of thing, modeled as bipartite graphs. That was like that was not there like when marriage theorem was invented. Okay. So if you recall one of the previous lectures, we talked about coloring, where we said that vertices can be colored. So what we did was that, for example, there are 5 people sitting in the first row, 1, 2, 3, 4, 5. The task for rest of the people is that we want to color all of them. The restriction is that, assuming that there's no like empty seat in between, those 5 are sitting next to each other. So we want to color all of them using different colors. What would be the most easy way of coloring all these 5 people using different colors? Or easier way, right? Okay, yeah. So if I like, if you say me that if 5 people, if I bring in 5 colors, so I can assign arbitrarily 1 color to each person, and they can paint themselves, and like every person will be having different color. But if the question is changed to that, what will be the minimum number of colors to paint these people such that no 2 adjacent people have the same color? And then your answer would be 2, because you use color 1, then color 2, then color 1, then color 2. You keep on alternate basis. So that like minimum number of colors is known as chromatic number, right? So this xg represents that chromatic number, that what is the minimum number of colors to color a graph such that no 2 adjacent vertices have the same color. Now, if you look at the bipyrite graph, its structure is quite beautiful because we know from its fundamental characteristic that no 2 vertices in this partition will be connected with each other. So we can blindly color all of them using the same color. And the vertices in the second partition are not mutually connected because it's a bipyrite graph. So we can use color number 2 for that one, and hence the minimum number of colors required to paint a bipyrite graph of any size is 2. Yeah. Say it again, sorry. It's no question is a stupid question. I didn't make any partition, right? I don't want to make partition in students. Okay. No. Okay. So the question which I tried to do was that let's assume that those 5 people are sitting next to each other. The task given to you was to paint their faces such that no 2 adjacent people have the same color. Did you get the point? Right. So 1.1, like one brute force or like easy or intuitive answer could be that I pick large number of colors, or maybe like same number of colors as those of people, and give them some, like I assign 1 bucket to everyone, and because all those buckets are different, they'll paint their faces. But because I'm interested in minimum number of colors, so another like intelligent idea was that I do it on alternate basis, right? So color 1, color 2, color 1, color 2 on alternate basis, right? But I can't like paint them using 1 color. So hence 2 is my minimum number of colors. Okay, go ahead. Yeah. Yeah. Okay. Yeah. There's no mutual connection between. No. So see, when I say they're next to each other, that means they're adjacent. Each person is a vertex. So these 2 persons are sitting next to each other. What does that mean in terms of graphs? Huh? They are adjacent, right? Adjacent means there is a direct edge between them. Connected means path, right? But adjacent means that there's only one edge between them, right? Which means, so when we say that no 2 adjacent vertices have to have same color, so you see, otherwise, so kahin na kahin path will be there from red to green vertices, no? So for example, I can give a try with some poor drawing over here. Let me try it. So if I start from here, oops. Okay, let me try to use this line. And now I'm following this line over here. It lands me here. So now these 2 red vertices are connected. There's a path. We didn't talk about path. We're talking about adjacency. Okay. Yes. See, technically this is a cycle because we can go this way and come back. More specifically, the cycle will be more intuitive if we think of a diagram like this one, right? It's just like, like, can you like go from here to the PDC and come back to SSC? So if there's only, if you're allowed to follow the same path in both directions, that's a cycle, right? Because you have returned back to the back to your home station. So if you write that sequence, you'll be writing SSC, comma PDC, comma SSC. So first and last are getting repeated, no intermediate is getting repeated. Was there a question here? No? Okay, let's move little forward. So okay, like the upper part of the slide is the previous slide. What about is C6 bipartite? C6 was a type of graph where 6 vertices are on one cycle, right? The kind of stuff over here. Is it bipartite? If you look at this, is C6 bipartite? You said no or yes? You said both. So you are like, you are using chromatic number as the trick to figure out, right? Okay, so this is yeah, I can go that way, which you are suggesting, or if I start with one is connected with 2, I throw 2 in the other partition. 2 is connected with, I throw 3 in the partition 1. 3 is connected with 4 goes here. I connect 4 with 5, 5 goes here. I connect 5 with 6, 6 goes here. Where is 6 connected with? With 1, it goes here. Right? Did I miss any vertex? Did I miss any edge? Is it bipartite? So will every cyclic graph be a bipartite graph? Yes. Excellent, right? This is a very smart observation. So, and that's where I was about to land in a while. So what if I try C5? So C5 is that I start with 1, go to 2, 2 is connected with 3, 3 is connected with 4, 4 is connected with 5 is connected with. So now see, this is the problematic edge. This has to fall within the same partition, which is not allowed. Does that make sense? So C5 is not bipartite. Or the suggestion which you gave at the start was that if I start coloring them in alternate colors, color 1, so I make every alternate vertex pink, and I use some other color to color the remaining vertices, like I make all of them blue. So 2, its chromatic number is 2 because all vertices got colored using 2 colors, where no 2 adjacent have the same color. So again, so this is another reason, but I can't do this thing for C5. C1 is like the chromatic number is 1, right? So that's not even bipartite because I can't create 2 partitions. So if you like, yeah, so if you have, you need to have at least 2 vertices in 2 separate partitions. Otherwise, one partition will be empty. Say it again. All non-cyclic. Perhaps yes. Yeah, I'm thinking. Perhaps yes. Okay, huh? Non-cyclic means that, like, if non-cyclic means actually, yeah, I'm थोड़ा सा आगे jump करेंगे, but non-cyclic means tree, right? Tree is bipartite. You're right. But we didn't study tree, right? Our next topic is trees. Okay, someone is trying to say, thank you. I'll wait for the coffee. Unfortunately, everyone is like seeing all these promises and commitments publicly, so people can see our messages like on the screen. They're very bad people. They're only having an eye on the messages, right? They're not looking at slides. So okay, for which CN is bipartite? When n is even, right? So we already figured out, so when n is not even, then it's not bipartite. Okay, second last thing, very quick. Now look at the last thing, right? So this is somewhat like related to what you were saying, that a graph is bipartite if and only if it contains no odd length cycles. The kind of intuition which we have built was using that C5 stuff. But like for a graph to be bipartite, it should not contain any cycle whose length is odd. What is odd length cycle? Number of vertices in the cycle are odd, right? So if that number is odd, then 2 vertices will be pushed in one partition, and they'll be connected as well because they're part of cycle. So that will cause this problem you saw in C5. Okay, so this is the last thing, and then we'll stop. Graph is bipartite. We have already figured out. So forget about the like textual part. What can you see in the first visualization on the leftmost side? There are two partitions. One is the upper partition. Instead of like drawing them in the left or right order, we have placed them over here. This is partition 1. The other one is partition 2. Is it a bipartite graph? Is the second one a bipartite graph? So if I'm sure if I asked you not to read the text, then I'm also sure you will definitely read the text. But like, what is the kind of characteristic in these visualizations? What could you see in these three visualizations? They're bipartite. What is special about them? All possible edges have been inserted. Very good, right? Which means that every vertex in one partition is connected with every vertex in the other partition. So if we generalize it as KMN, which means m number of vertices in one partition, n number of vertices in the other partition. So for out of these m vertices, for each of them, there are n outgoing edges. Directly, sorry, if I said connected, that might be a like loosely clarified term. I mean adjacent, right? So that means, which means you're directly connected. When I say directly connected, that means we're talking about edges, right? So how many edges are there in KMN? KMN क्या है? It has two subscripts. What was K at the start? Complete graph. Over there, we used to talk about K5, K6. Now we are putting two subscripts because we have two partitions. And the number of edges between those two partitions are going to be all maximum possible edges, and their count is Mn. Very good. So that's it for today. Thank you very much. So